Right now, as you settle into your bed and feel the weight of your blanket pressing gently against your body, there is another weight you can't feel at all. The air around you, the atmosphere that extends for miles above your head, is pressing down on every square inch of your skin with a force of about 14.7 pounds. This is the weight of the sky, the column of air that stretches from the ground all the way to the edge of space. You don't notice it because your body pushes back with exactly the same pressure. You are balanced with the world around you. The air inside you, the air in your lungs, in your cells, in your blood, pushes outward with that same 14.7 pounds per square inch. This balance is why you don't feel crushed. This balance is why you can walk, breathe, and exist without even thinking about the weight above you. But here is something worth sitting with for a moment.
If the atmosphere above you were replaced with water, and you descended even a little way beneath the surface, that balance would disappear. Water is much, much heavier than air. A column of water just 33 feet tall weighs as much as the entire column of air above you. That means for every 33 feet you go down, the pressure on your body increases by another 14.7 pounds per square inch. At 100 feet, you are feeling 4 times normal pressure. At 1,000 feet, you are feeling 30 times normal pressure. And at the deepest point in the ocean, nearly 7 miles down, the pressure is over 1,000 times what you feel right now. To put that number in perspective, imagine the weight of an entire school bus pressing down on every single square inch of your skin. That is what the deep ocean feels like. That is the reality of a place that covers more of our planet's surface than all the continents combined. And yet, somehow, there is life down there. Somehow, there are creatures that thrive under that crushing weight. And somehow, humans have learned to go there too. This is the story of how we did that. It is not a story about the creatures of the deep, though they are part of it. It is a story about engineering, about physics, about the human drive to see what lies in the darkest, most inaccessible places on Earth. It is a story about building machines that can do what our bodies cannot. Machines that can survive pressure that would turn steel into tinfoil and bone into powder. Machines that can carry human beings into a world where no sunlight has ever reached, where the temperature hovers just above freezing, and where any mistake is instantly fatal. The story begins not at the bottom of the ocean, but on the surface. It begins with a question that has driven inventors, engineers, and explorers for generations. That question is simple. How do you build something that can withstand the weight of 7 miles of water without being crushed? And before we can answer that question, we have to understand exactly what we are up against. We have to understand pressure, not as an abstract concept, but as a physical reality. Pressure is not just a number on a gauge, it is a force that pushes from every direction simultaneously. It doesn't care about your intentions, it doesn't care about your courage, it only cares about the laws of physics. If you take a hollow steel ball and lower it into the ocean, the water pushes against it from all sides. The deeper you go, the harder the water pushes. At a certain point, the steel begins to bend. The ball begins to deform. If you go even deeper, the steel gives way entirely and the ball collapses like a soda can under a heavy foot. This is called implosion, and it happens in a fraction of a second. One moment the ball is intact. The next moment, it is a crumpled mess of metal. The key to preventing this is shape. A sphere is the strongest shape for resisting pressure. It distributes the force evenly across its entire surface. There are no corners, no flat spots, no weak points where pressure can concentrate and cause failure. This is why deep-sea submersibles are almost always spheres. They are not convenient shapes for fitting people or equipment, but they are the only shapes that can reliably survive the deep. The materials matter too. Not all steel is equal. For deep-sea applications, you need steel that is incredibly strong, incredibly pure, and incredibly carefully constructed. The walls of a submersible sphere must be thick enough to withstand the pressure, but thin enough to keep the vessel light enough to float. This is a delicate balance. Too thick, and the vessel sinks. Too thin, and it crushes. There is also the matter of the windows. Every submersible needs a way to see out.
That means cutting holes in the sphere for windows. Those holes are weak points. They are where pressure finds its easiest path to failure. The windows have to be made of something strong enough to withstand the pressure, but transparent enough to allow vision. This is why deep-sea windows are small, thick, and made of a very special material. Often, they are made of quartz or tempered glass, carefully designed and tested to survive pressures far beyond what they will ever experience. Testing is another crucial part of the process. Before any submersible ever touches the ocean, it must be tested. Engineers place it in a pressure chamber and simulate the conditions of the deep. They pressurize the water around it to the equivalent of 7 miles down. They watch closely. They listen. If something cracks, they find out on the surface, where it is survivable, rather than in the deep, where it is not. So, here is where we find ourselves at the beginning of our story.
The problem has been stated clearly. The solutions are emerging from the work of engineers across many decades. But before we can see how those solutions came together, we have to ask one more question, a question that is perhaps the most important one of all. Why did anyone even try? Why did humans decide to venture into a place that was clearly not made for them? Why did they spend vast sums of money and years of effort to build machines that could survive the impossible pressure of the deep? What drove them to take that risk? The answer, in many ways, is as old as humanity itself. Curiosity. The simple, unquenchable desire to see what lies beyond the next horizon. For centuries, the horizon was a line on the surface of the ocean. People sailed across it to discover new lands. But eventually, the surface was fully mapped. The horizons had all been crossed. There was nowhere left to go on the surface, so humanity turned its gaze downward. But curiosity was not the only driver.
There was also fear. The Cold War brought a new urgency to deep-sea exploration. Submarines became weapons of immense power. They could hide beneath the waves, carrying nuclear missiles that could end civilization. If one of those submarines sank, it could not simply be abandoned. It carried secrets. It carried nuclear fuel. It carried the bodies of its crew. Finding and recovering these submarines became a matter of national security. And that required the ability to reach the bottom. This combination of curiosity and necessity is what pushed the engineering forward. The first deep-sea submersibles were built with government money, often military money. They were designed for military purposes, but they ended up serving science as well. The tools built for war became tools for discovery. And with each new discovery, the value of deep-sea exploration became clearer. There is one more question that we must ask before we move forward. It is a question that sits at the heart of everything we are about to explore. What did we find when we finally got there? What was waiting for us in the darkness, under all that pressure, in that impossible place? And perhaps the answer to that question is the most surprising thing of all. We found life. Not just a little life, but a vibrant, thriving ecosystem.
we found creatures that had evolved to live under conditions that we thought were completely uninhabitable. We found a world that existed entirely without sunlight, powered not by photosynthesis but by chemistry. We found a place that challenged everything we thought we knew about life on Earth. And that discovery, in turn, raised even more questions. Questions about the origins of life. Questions about the possibility of life on other worlds. Questions about the resilience of nature and the limits of adaptation. But we are getting ahead of ourselves.
Before we can reach that place, we have to build the machines that can take us there. We have to solve the engineering problem. We have to learn how to build vessels that can withstand the weight of the world. In the chapters that follow, we will follow the journey of these machines. We will start with the earliest attempts, the primitive diving bells and pressurized suits that could barely reach a few hundred feet. We will move through the development of the Bathysphere, a steel ball lowered on a cable, which first let humans see the deep with their own eyes. We will explore the invention of the Bathysphere, a floating vessel that could reach depths far beyond anything before it. And we will arrive at the submersibles of today, sophisticated machines that can dive for hours, maneuver with precision, and bring back samples and images from the very bottom of the ocean. But this is not just a story of machines. It is a story of people, of the engineers who designed them,
Of the pilots who risked their lives to fly them, of the scientists who used them to make discoveries that changed the world. It is a story of determination, of ingenuity, and of courage. And it all begins with a simple, fundamental problem: pressure. The weight of the ocean above us. The force that wants to crush everything that descends into its depths. The problem that we had to solve before we could ever hope to see what lies beneath. In the next chapter, we will meet the men who built the first machine that could truly reach the deep. We will watch as they descend into the abyss, knowing that the only thing standing between them and certain death is a steel sphere 2 inches thick. We will see what they saw, and we will begin to understand just how vast and mysterious this place truly is. But for now, let us sit with the weight of what we have learned. Let us feel in our imaginations the pressure of the deep. Let us appreciate the incredible engineering that makes it possible to go there. And let us prepare to descend into the unknown. The deep ocean is waiting, and it has much to show us. In the early 1930s, the world was gripped by the Great Depression. Banks were failing, businesses were closing, and millions of people were out of work. Hope was a scarce commodity. But in the midst of all that hardship, 2 men were building something that would inspire the world. They were building a machine that would allow human beings to see the deepest parts of the ocean for the very first time. Their names were William Beebe and Otis Barton. Beebe was a naturalist, a man who had spent his life studying birds and animals. He had traveled the world, climbed mountains, and explored jungles. But his greatest passion was the ocean. He wanted to understand what lived beneath the waves, especially in the deep, dark places that no one had ever seen. Barton was an engineer. He came from a wealthy family and had studied engineering at Harvard. He shared Beebe's fascination with the deep sea. He also had the resources to do something about it. He offered to fund the construction of a deep-sea diving vessel, a machine that could carry people down into the abyss. The machine they built was called the Bathysphere. The name comes from the Greek words for deep and sphere, and that is exactly what it was. A steel sphere just under 5 feet in diameter, with walls 2 inches thick. It was designed to carry 2 people to depths that had never been reached before. The Bathysphere was not a submarine. It did not have engines or propellers. It was lowered into the ocean on a steel cable, like a bucket into a well. It was a simple machine, but it was a marvel of engineering. The steel sphere weighed about 2.5 tons. That is roughly the weight of a large SUV. The walls were made of hardened steel, forged to be as strong as possible.
The sphere had 3 small windows, each made of fused quartz, which is one of the strongest transparent materials known at the time. Each window was 3 inches thick and 8 inches in diameter. Inside the sphere, the space was incredibly cramped. The diameter of the sphere was only 4.5 feet. 2 men could fit inside, but they would have to sit very close together. There were oxygen tanks, chemical canisters to absorb carbon dioxide, and a fan to circulate the air. That fan was powered by a hand crank. One of the men would have to turn the crank to keep the air from becoming stagnant. The sphere was sealed with a heavy door, secured by 10 bolts. The bolts had to be tightened from the outside, so once the door was closed, the men inside could not open it. They were completely dependent on the crew on the surface to bring them back up. The bathysphere was a risk, a huge risk.
If anything went wrong, if the cable snapped, if the steel cracked, if the windows shattered, the men inside would be lost forever. There was no rescue possible at those depths. The ocean simply would not allow it. But Beebe and Barton were not deterred. They believed in their machine. They believed in the engineering. And they were driven by a passion for discovery that outweighed the fear. The first test dives were conducted in the summer of 1930, off the coast of Bermuda. The bathysphere was lowered into the water, and Beebe and Barton climbed inside. The air was hot and humid. The sphere was painted black to protect the paint from the salt water, and the interior was dark, illuminated only by a single light bulb. As the sphere descended, Beebe looked out through the quartz window. The water began to change color. First it was blue, then green, then a deep indigo. The sunlight faded, and the world outside grew darker. Beebe watched as tiny organisms, glowing with their own light, drifted past the window like falling stars. He recorded everything he saw in a notebook, speaking into a telephone that was connected to the surface by a wire running along the steel cable. The first dive reached a depth of 800 feet. It was a record. No human had ever gone that deep before. But Beebe and Barton were not satisfied. They wanted to go deeper. Over the next several years, they made more dives. They reached 1,000 feet, then 2,000 feet. Each dive pushed the boundaries of what was possible, and each dive revealed something new about the deep ocean. Beebe's observations were groundbreaking. He saw fish with glowing organs, jellyfish that pulsed with bioluminescent light, and strange creatures that had never been seen before. He described them in vivid detail. His words painted a picture of a world that was alien and beautiful. He also noted the silence.
The deep ocean, he wrote, was a place of profound quiet. The only sounds were the creaking of the steel sphere and the crackling of the telephone wire. It was a world without wind, without waves, without the noise of surface life. A world of pure stillness. The deepest dive of the bathysphere took place on August 15th, 1934. Beebe and Barton descended to 3,028 feet. It was a remarkable achievement. The bathysphere had proved that humans could survive at great depths. It had opened a window onto a world that had been hidden for millions of years. But the bathysphere also had limitations. It could not move. It could not change direction. It could only go down and come back up. And its depth was limited by the length of the cable. Beebe and Barton wanted to go deeper. They dreamed of reaching 5,000 feet, then 10,000 feet. But the bathysphere could not take them there. The cable would have to be longer
and stronger. The sphere would have to be built differently, and there were risks that even the most daring explorer would hesitate to take. The Bathysphere project came to an end in the late 1930s. Beebe continued his work as a naturalist, writing books and giving lectures. Barton went on to design other deep-sea vessels, but the legacy of the Bathysphere lived on. It had proven that deep-sea exploration was possible. It had shown that humans could survive the crushing pressure of the abyss, and it had captured the imagination of the world. The Bathysphere also introduced a crucial concept that would shape all future deep-sea vessels: the concept of the sphere. The Bathysphere was a steel sphere, and it worked because a sphere is the strongest shape for resisting pressure. Every deep-sea submersible since then has used a spherical pressure hull. It is a design that has been proven again and again, from the early Bathysphere to the modern submersibles that dive to the bottom of the ocean today. The Bathysphere was not a submarine. It was a diving bell, a capsule lowered on a cable. But it laid the groundwork for everything that followed. It proved that the deep ocean could be explored. It inspired a generation of engineers, scientists, and adventurers. And it marked the beginning of a new era in human exploration. In the years after the Bathysphere, Beebe and Barton continued to push the boundaries of deep-sea research. Beebe wrote extensively about his experiences, describing the wonders he had seen in the deep. His books were widely read and inspired many others to take up the study of oceanography. Barton, meanwhile, continued to innovate. He designed a new type of deep-sea vehicle, one that could move independently of a surface cable. But that is a story for another chapter. The Bathysphere also had a profound cultural impact. It was a symbol of human ingenuity, a reminder that even in the darkest depths, we can find light. It showed that the ocean is not a barrier but a frontier, and it proved that with enough determination and creativity, we can overcome any obstacle. So, the next time you look out at the ocean, think of Beebe and Barton. Think of the two men in a steel sphere, descending into the unknown. Think of the courage it took to climb inside that sphere, knowing that they might never return. And think of the wonder they felt when they saw the deep ocean for the first time. The Bathysphere was a beginning. It was the first true descent into the abyss, but it was far from the last. The deep ocean still holds many secrets, and we are still exploring its depths. And the story of how we got there is a story of ingenuity, courage, and an unquenchable thirst for discovery. As we close this chapter, let us ask ourselves a question. What would it have been like to be inside that sphere? To feel the weight of the ocean pressing in from all sides? To see the blackness of the abyss and the flickering lights of unknown creatures? To be the first person to lay eyes on a world that no one had ever seen before? That is the question that drove Beebe and Barton. And it is the question that continues to drive us today. The deep ocean is a place of mystery and wonder, and we are only beginning to understand it. So, let us continue our journey. Let us descend further into the abyss, past the limits of the Bathysphere, into the depths that Beebe and Barton could only dream of. And let us discover what lies there, in the darkest, most inaccessible places on Earth. The ocean is calling, and we must answer. By the late 1940s, the Bathysphere had pushed human exploration to depths of just over 3,000 feet. It was an incredible achievement, but it was also a limit. The steel cable that held the Bathysphere could only be so long. Every foot of cable added more weight, more drag, and more risk. Beyond 3,000 feet, the cable itself became a liability. It could snap, tangle, or simply stretch too much under its own weight.
To go deeper, something entirely new was needed. Not a sphere hanging on a cable, but a vessel that could descend and ascend on its own. A vessel that carried its own buoyancy. A vessel that could float. That was the idea behind the Bathysphere. The word comes from the Greek words for deep and vessel. It was coined by a Swiss physicist and engineer named Auguste Piccard. Piccard was a remarkable man. He had already made a name for himself by flying to the stratosphere in a balloon, reaching altitudes that no one had ever achieved. He understood how to survive in extreme environments, and he understood that the principles of balloon flight could be applied to deep-sea exploration. Here is the core idea.
A balloon rises because it is filled with a gas that is lighter than the surrounding air. The gas provides buoyancy. A bathyscaphe works on the same principle but underwater. Instead of a gas, it uses a liquid that is lighter than seawater. The liquid is typically gasoline. Yes, gasoline. It is lighter than water. It is incompressible, and it does not react with the surrounding environment. The bathyscaphe consists of two main parts. The first is the float, a large tank filled with gasoline. The float provides the buoyancy that keeps the vessel afloat at the surface and allows it to descend and ascend. The second is the pressure sphere, a steel capsule that houses the crew. The sphere is attached to the bottom of the float. It is the same principle as the bathysphere, but now the sphere is part of a self-contained vehicle. The float is not a solid tank. It is open at the bottom, allowing seawater to enter as the vessel descends.
The gasoline, being lighter than water, stays on top and provides buoyancy. As the vessel descends, the float is compressed by the pressure, but the gasoline remains incompressible, so the buoyancy is maintained. When the vessel wants to ascend, it releases ballast, which is typically small steel pellets or iron shot. This reduces the overall weight, and the vessel rises back to the surface. The bathyscaphe was a brilliant design. It solved the cable problem. It could descend to depths that were previously unimaginable, and it gave the pilot control over the vessel's movement. The first bathyscaphe, called the FNR-S2, was built in Belgium and tested in 1948. It reached a depth of nearly 1 mile, around 4,500 feet. It was a success. But the FNR-S2 was a test vehicle, not a fully operational vessel. The second bathyscaphe, called the Trieste, was built in Italy and launched in 1953. It was the first bathyscaphe designed for serious exploration. It was larger, more powerful, and more capable than its predecessor. It was also the vessel that would eventually take humans to the very bottom of the ocean. The Trieste was a marvel of engineering. The float was nearly 50 feet long and 12 feet wide. It was filled with 22,000 gallons of gasoline. The pressure sphere was attached to the bottom of the float. It was made of steel, with walls nearly 5 inches thick. The interior was just over 6 feet in diameter, enough space for 2 people. The Trieste was also equipped with a powerful electric motor and propellers. It could move horizontally, albeit very slowly. It had lights, cameras, and a mechanical arm for collecting samples. It was a fully functional submersible. In 1953, the Trieste made a series of test dives in the Mediterranean Sea. It reached depths of over 10,000 feet. It was a record, but the Trieste was still being developed. It was not yet ready for its ultimate goal. That goal was the deepest point in the ocean, a place called the Challenger Deep, located at the southern end of the Mariana Trench. The Challenger Deep is nearly 7 miles deep, over 36,000 feet. It is the lowest point on Earth's surface.
To put that in perspective, if you took Mount Everest, the tallest mountain on Earth, and dropped it into the Challenger Deep, its summit would still be over a mile underwater. That is how deep it is. No human had ever been to the Challenger Deep. No human had ever been anywhere close. The pressure there is over 8 tons per square inch. That is enough to crush a steel submarine like a soda can. It was a place that seemed impossible to reach. But Auguste Piccard and his son Jacques were determined to try. They had built the Trieste, they had tested it, and they knew it could reach the bottom. The dive was scheduled for January 23, 1960. The target was the Challenger Deep, near the island of Guam in the Pacific Ocean. The Trieste was loaded onto a barge and towed to the site. The crew was Jacques Piccard and Lieutenant Don Walsh of the United States Navy. The morning of the dive was calm. The sea was still. The Trieste was lowered into the water and the 2 men climbed inside. The interior was cramped, dark, and cold. They settled in for what would be a long, tense journey. The descent began at around 8 in the morning. The Trieste was designed to descend at a rate of about 3 feet per second. At that speed, it would take nearly 5 hours to reach the bottom. It was a long time to be confined in a tiny metal sphere. As the Trieste descended, the men watched the world outside change. The water grew darker, then black. The temperature dropped. The pressure increased. They could hear the steel hull creaking and groaning under the strain. It was an unnerving sound, but it was normal. The steel was designed to withstand the pressure. It was just a reminder of how much weight was pressing against them. At around 30,000 feet, the instruments began to show signs of trouble. One of the windows cracked. Not the glass, but the seal. A small crack appeared in the outer layer of the quartz window. It was not a structural failure, but it was enough to cause concern. The crack was caused by the pressure, and it meant that the window had been weakened. Piccard and Walsh made a decision. They would continue. They had come too far to turn back. They trusted the window. They trusted the design. They trusted their luck. At 11 in the morning, after nearly 5 hours of descent, the Trieste touched the bottom. The depth gauge read 35,797 feet. It was the deepest point on Earth. It was the bottom of the Mariana Trench. Piccard and Walsh looked out through the window.
They saw a world that no human had ever seen. The bottom was covered in a fine, grey mud. There were small creatures, like shrimp, swimming through the water. There were also a few larger animals, including what appeared to be a flatfish. It was a stunning revelation. Life existed at the bottom of the ocean. Not just microscopic life, but visible, recognizable animals. The deep ocean was not a sterile desert. It was a living world. Piccard and Walsh spent about 20 minutes on the bottom. They observed, took photographs, and collected samples. They made notes. They spoke to the surface via a telephone line that ran up the length of the Trieste's float. Then they began their ascent. The Trieste released its ballast and began to rise. It took nearly 4 hours to reach the surface. It was a long, slow journey back to the world of light and air. When they surfaced, the men were greeted with applause and congratulations. They had made history. They had shown that humans could survive at the deepest point on Earth. They had opened up a new frontier. The Trieste's dive was a triumph of engineering and courage. It proved that the deep ocean was accessible. It proved that the design of the Bathysphere worked, and it inspired a new generation of explorers and engineers to push even further. But the Trieste's dive was also a one-time event. The Trieste was not designed for frequent dives. It was a test vehicle, a proof of concept. After the dive, it was retired from active service. It now sits in a museum. The Trieste's legacy is not its steel sphere or its gasoline float. It is the knowledge that the deep ocean is reachable. It is the proof that humans can go there. And it is the inspiration for everything that followed. In the years after the Trieste's dive, a new generation of deep-sea vehicles was built. They were smaller, lighter, more maneuverable. They could dive more often and stay down longer.
They could carry scientists to study the wonders of the deep. These new vehicles were not bathyscapes, they were submersibles. They were more like small submarines than floating spheres. They could move independently, both horizontally and vertically. They had powerful lights and cameras. They could collect samples and conduct experiments. The most famous of these submersibles was the Alvin. Built in 1964, the Alvin has been used for countless deep-sea explorations. It has discovered hydrothermal vents, studied deep-sea ecosystems, and explored shipwrecks like the Titanic. It has carried thousands of scientists on thousands of dives. The Alvin is still in service today. It has been upgraded and modified many times. It can now dive to over 15,000 feet. It is a symbol of American innovation and scientific curiosity. So, the Trieste's dive was a milestone. It was the moment when humans first touched the bottom of the ocean.
It was the moment when the deep ocean ceased to be a mystery and became a place of exploration. But there is more to the story. The Trieste's dive was not the end. It was just the beginning. The deep ocean is still full of secrets. There are still depths to explore and creatures to discover. And each new dive brings us closer to understanding this vast, hidden world. So, let us continue our journey. Let us descend once more into the abyss. Let us see what else lies there, in the darkness and the cold. Let us discover what other wonders the deep ocean has to offer. The Trieste showed us that we can go to the bottom. Now we must learn what we can find there. The Trieste's historic dive in 1960 proved that humans could reach the bottom of the ocean. But the Trieste was a massive, unwieldy vehicle. It was designed for one purpose: to go as deep as possible. It was not designed for frequent dives, nor was it designed for scientific research.
It was a one-time achievement, a milestone that would stand for decades. What was needed was a new kind of vehicle, something smaller, lighter, and more maneuverable. Something that could carry scientists to the deep sea and allow them to work there for hours at a time. Something that could be used repeatedly, dive after dive, year after year. Something that would turn the deep ocean from a place of brief visits into a place of sustained exploration. That vehicle was the Alvin. The Alvin was conceived in the early 1960s, a time of great optimism and ambition. The United States was engaged in a space race with the Soviet Union, but there was also a growing interest in exploring the ocean. The National Science Foundation, a government agency that funds scientific research, saw the need for a dedicated deep-sea submersible. They commissioned the Woods Hole Oceanographic Institution in Massachusetts to design and build it.
The Alvin was named after Alan Vine, a prominent oceanographer who had been instrumental in its development. It was built in 1964 and launched that same year. It was a revolutionary vehicle. The Alvin is relatively small, only about 23 feet long. It weighs about 17 tons. It can carry a pilot and 2 scientists. It has a top speed of about 2 knots, which is roughly 2 miles per hour. It can dive to a depth of over 15,000 feet, nearly 3 miles down.
The Alvin's pressure hull is a sphere, just like the Bathysphere and the Trieste. It is made of titanium, a lightweight and incredibly strong metal. The sphere is about 6 feet in diameter, which is just enough room for 3 people to sit comfortably. The walls are nearly 3 inches thick, designed to withstand pressures of over 6,000 pounds per square inch. The Alvin is powered by batteries, not by a gasoline float. It has electric motors that drive propellers, allowing it to maneuver precisely. It has lights, cameras, and a variety of scientific instruments. It also has a mechanical arm that can collect samples from the seafloor. The Alvin was designed to be a scientific research vessel. It was not just a vehicle for reaching the deep. It was a laboratory for studying it. Scientists could collect rocks, water samples, and biological specimens. They could observe animals in their natural habitat. They could conduct experiments in situ, at the bottom of the ocean. The Alvin's first dives were in 1964 and 1965. They were test dives, designed to prove that the vehicle was safe and functional. The Alvin reached depths of over 6,000 feet. It was a success. But the Alvin's true significance became clear in the years that followed. It was used for a remarkable series of scientific discoveries that would change our understanding of the deep ocean forever. One of the most important discoveries made by the Alvin was the existence of hydrothermal vents. These are underwater geysers, cracks in the sea floor where superheated water, rich in minerals, erupts from the Earth's interior. The water can reach temperatures of over 600 degrees Fahrenheit. It is so hot that it would melt lead. The Alvin first encountered hydrothermal vents in the late 1970s during a series of dives in the Pacific Ocean. The discovery was accidental. The scientists were looking for geological features, not vents. But what they found was far more extraordinary. The vents were surrounded by a dense community of life. They were giant tube worms, some over 6 feet long. They were unlike any creature seen before. They had no mouth, no stomach, no digestive system. They were filled with bacteria that converted the minerals in the vent water into food. The bacteria provided the tube worms with all the nourishment they needed. There were also enormous clams, some as big as dinner plates. There were crabs, shrimp, and a variety of other animals. It was a thriving ecosystem, completely independent of the sun. The energy came not from sunlight, but from the Earth itself. This was a profound discovery. It overturned the conventional wisdom that all life on Earth depended on photosynthesis. It showed that life could exist in complete darkness, powered by chemical energy. It opened up new possibilities for the search for life on other planets. The Alvin was also used to explore the wreck of the Titanic. In 1986, a team led by Robert Ballard, a renowned oceanographer, used the Alvin to dive to the Titanic, which lies 12,000 feet below the surface of the Atlantic Ocean. The Alvin captured the first detailed images of the wreck, revealing its location and condition. The Titanic expedition was a powerful demonstration of the Alvin's capabilities. The vehicle descended to the wreck, maneuvered around it, and captured footage that would be seen by millions of people around the world. It brought the tragedy of the Titanic back to life, and it cemented the Alvin's place in history. The Alvin has been upgraded many times over the years. In the 1970s, it was fitted with a new titanium sphere that could reach greater depths. In the 1980s, its electronics were upgraded. In the 1990s, its batteries were replaced. Each upgrade extended the Alvin's capabilities and allowed it to continue its work. Today, the Alvin is still in service. It has completed over 5,000 dives. It has carried more than 3,000 scientists to the deep ocean. It has been used for a wide range of research, from studying hydrothermal vents to exploring deep-sea ecosystems. The Alvin is not the only deep-sea submersible in existence. There are others, built by other countries. Russia has the Mir submersibles, which can reach depths of nearly 20,000 feet. Japan has the Shinkai, which can reach over 21,000 feet. France has the Nautil, which can reach over 19,000 feet. But the Alvin is the most famous. It is the symbol of American deep-sea exploration. It has been featured in countless documentaries and news stories. It has inspired generations of scientists and engineers. The Alvin's legacy is not just its discoveries, it is also its design. The Alvin is a small, maneuverable, scientifically focused submersible. It is the model for all modern deep-sea vehicles. It has proven that deep-sea exploration is not just possible, but practical. The Alvin has also shown that deep-sea exploration is not just about reaching the bottom. It is about understanding the bottom. It is about studying the animals, the rocks, the water, the chemistry. It is about answering questions that have puzzled scientists for centuries. And there are still many questions to answer. The deep ocean is vast, covering more than half the Earth's surface. We have explored only a tiny fraction of it. We have only a rough map of the seafloor. We have only a partial inventory of the species that live there. Every time the Alvin dives, it brings back new information. Every dive reveals something new, a new species, a new ecosystem, a new geological formation, a new chemical process. The deep ocean is still full of secrets, and the Alvin is still helping to uncover them. So, the Alvin is not just a machine, it is a symbol of human curiosity and ingenuity. It is a tool that has allowed us to explore the deepest, darkest, and most inaccessible places on our planet. It is a vehicle of discovery. As we continue our journey, we will explore some of the Alvin's most remarkable discoveries. We will meet the creatures that live in the deep, see the ecosystems that exist in the darkness, and understand the geological forces that shape the ocean floor. The Alvin has shown us what is possible. It has opened our eyes to a world that was once hidden from view, and it has inspired us to continue our exploration. So, let us descend once more into the abyss. Let us join the scientists and pilots of the Alvin. Let us see what lies beneath the waves. The deep ocean is waiting, and it has much to show us. The year was 1977. The place was the Galapagos Rift, a volcanic ridge on the floor of the Pacific Ocean, about 250 miles off the coast of Ecuador. A team of scientists was on board the research vessel Nor, preparing for a series of dives in the submersible Alvin. Their goal was to study the geology of the ocean floor. They wanted to understand how the Earth's crust was formed at the mid-ocean ridges, where tectonic plates are pulling apart. What they found was far more extraordinary than they ever expected. The first dive was on February 15, 1977. The Alvin descended through the dark water, past 3,000 feet, past 5,000 feet, until it reached the bottom at nearly 8,000 feet. The scientists peered through the viewports, expecting to see the rocky, barren seafloor that was typical of such depths. Instead, they saw something completely unexpected. A shimmering, ghostly landscape, filled with life. There were giant tube worms, some over 6 feet long, their red plumes waving in the current. There were clams the size of dinner plates. There were mussels, crabs, and shrimp. There were fields of white bacteria covering the rocks like snow. It was a dense, vibrant ecosystem teeming with life. The scientists were stunned. They had never seen anything like it. The deep ocean was supposed to be a desert, a place of near-zero life. But here, in the middle of the abyss, was a thriving community of animals.
The key to the mystery was the water. The Alvin sensors showed that the water near the seafloor was unusually warm. It was also rich in chemicals, particularly hydrogen sulfide. The water was not coming from the surface. It was coming from the Earth itself.
It was being heated by volcanic activity deep beneath the crust. The scientists had discovered hydrothermal vents. They are essentially underwater geysers, cracks in the seafloor where superheated water, laden with minerals, erupts from the Earth's interior. The water can reach temperatures of over 600 degrees Fahrenheit, hot enough to melt lead. It is rich in hydrogen sulfide, methane, and other chemicals that are toxic to most forms of life. But for some organisms, these chemicals are not poison. They are food. The tube worms, for example, have no mouth, no stomach, no digestive system. Instead, they are filled with bacteria that live in their tissues. The bacteria convert the hydrogen sulfide in the vent water into organic matter, which provides the tube worms with nourishment. The tube worms provide the bacteria with a safe place to live. It is a symbiotic relationship, a partnership that allows both organisms to survive. The clams have a similar arrangement. They too host bacteria in their tissues. The bacteria supply them with nutrients, and the clams provide them with shelter. The shrimp and crabs feed directly on the bacteria. They graze on the bacterial mats that cover the rocks. They also feed on the tube worms and clams, or on the organic matter that drifts down from the vents. The entire ecosystem is powered by chemical energy, not by sunlight. The bacteria are the primary producers, the foundation of the food chain. They are the plants of the deep, but they do not photosynthesize, they chemosynthesize. They use the energy from chemical reactions to produce food. This was a profound discovery. It overturned the conventional wisdom that all life on Earth depends on the sun. It showed that life could exist in complete darkness, powered by the Earth's internal heat. It opened up new possibilities for the search for life on other planets. The discovery of hydrothermal vents was also a major breakthrough in our understanding of the deep ocean. It showed that the ocean floor is not a barren wasteland. It is a dynamic, active place, full of life and energy. The scientists who made the discovery were not expecting it. They were looking for geological features, not biological ones. But they were observant and curious. They noticed the unusual water temperatures and chemical signatures. They followed the clues and uncovered a new world. The hydrothermal vents are also important for understanding the Earth's climate. They are a significant source of heat and chemicals for the ocean. They influence the chemistry of the water and the distribution of nutrients. They play a role in the global carbon cycle and the regulation of the Earth's temperature. The vents are also a reminder of how much we still have to learn about our planet. The deep ocean is vast and largely unexplored. We have only a rough map of the seafloor. We have only a partial inventory of the species that live there. Every new dive brings new discoveries. The hydrothermal vents are also a source of inspiration. They show that life can thrive in the most extreme environments. They show that the universe is full of surprises. They encourage us to keep exploring, to keep asking questions, and to keep pushing the boundaries of knowledge. In the years since their discovery, hydrothermal vents have been found in many parts of the world. They are located at mid-ocean ridges where tectonic plates are pulling apart. They are also found at volcanic arcs and back arc basins. They are a global phenomenon. Each vent field is unique. The water temperature, chemical composition, and biological communities vary from site to site. Some vents are dominated by tube worms, others by clams or mussels. Some vents are hot, others are cooler. But all share one thing in common. They are powered by chemical energy,
not by sunlight. The study of hydrothermal vents has become a major field of research. Scientists from many countries are studying these unique ecosystems. They are exploring the biology, chemistry, and geology of the vents. They are learning about the origins of life, the evolution of species, and the functioning of the Earth system. Hydrothermal vents are also important for the search for life on other planets. They provide a model for how life could exist in the subsurface oceans of icy moons like Europa and Enceladus. If there is life on those worlds, it may be similar to the life found at hydrothermal vents. It would be dependent on chemical energy, not sunlight. So, the discovery of hydrothermal vents was a major milestone in the history of deep-sea exploration. It changed our understanding of the ocean and the Earth. It opened up new scientific frontiers, and it inspired a new generation of explorers and scientists. The Alvin played a crucial role in this discovery. It was the vehicle that carried the scientists to the sea floor. It was the tool that allowed them to see the vents for the first time. It was the instrument that collected the samples and measurements that proved the vents were real. The Alvin continues to be used for vent research today. It has visited many vent fields, from the Pacific to the Atlantic to the Indian Ocean. It has collected thousands of samples and made countless observations. It is one of the most important tools in the study of the deep ocean. And as we continue our journey, we will explore the hydrothermal vents in more detail. We will meet the creatures that live there. We will understand the processes that power them. And we will appreciate the remarkable world that exists beneath the waves. But the discovery of hydrothermal vents was just the beginning. There are still many secrets hidden in the deep ocean. There are still new species to discover, new ecosystems to explore, and new processes to understand. The exploration of the deep ocean is an ongoing adventure. So, let us continue our descent. Let us dive deeper into the abyss. Let us see what else lies there, in the darkness and the cold. The hydrothermal vents are just one chapter in the story of the deep ocean. There is much more to discover. The deep ocean is a world of extremes. The temperature is near freezing. The darkness is absolute. Food is scarce. But the most extreme feature of all is the pressure. At the bottom of the ocean, the pressure is over 1,000 times greater than at the surface. It is a force that would crush a human being instantly.
It is a force that would crush most machines, and yet, somehow, life thrives there. How is this possible? How do creatures survive in an environment that is so hostile to life as we know it? The answer lies in the remarkable adaptations that deep-sea organisms have evolved over millions of years. These adaptations allow them to withstand the crushing pressure, the extreme cold, and the scarcity of food. They are a testament to the power of evolution. Let us start with the most basic adaptation, the lack of air spaces. Air is compressible. At high pressures, air is squeezed into a much smaller volume. This is why your ears pop when you descend in an aeroplane or a submarine. The air in your middle ear is compressed, and you feel the pressure difference. Deep-sea creatures have evolved to avoid air spaces. They have no swim bladders, which are air-filled sacs that many fish use to control their buoyancy. Instead, they rely on other mechanisms, such as oil-filled sacs or specialized tissues. They have no lungs, only gills. Their bodies are made mostly of water and soft tissues, which are incompressible. This lack of air spaces means that deep-sea creatures are not crushed by the pressure. The pressure is applied equally to all parts of their bodies. There is no pressure difference between the inside and the outside. They are in equilibrium with their environment. Another important adaptation is the modification of proteins. Proteins are the building blocks of life. They perform a vast array of functions, from catalyzing chemical reactions to transporting molecules to providing structural support. But proteins are sensitive to pressure. At high pressures, they can unfold, losing their shape and function. Deep-sea creatures have evolved proteins that are more stable under pressure. These proteins have adapted to the high-pressure environment.
They maintain their shape and function, even under the crushing weight of the ocean. This adaptation is not limited to animals. Microbes, the single-celled organisms that are the foundation of the deep-sea food chain, also have pressure-adapted proteins. They are able to survive and thrive in an environment that would be lethal to most other organisms. The cold is another factor that shapes deep-sea life. The water temperature in the deep ocean is typically near 39 degrees Fahrenheit, just above freezing. This is a constant, unchanging temperature. There are no seasonal variations, no daily fluctuations. The cold slows down the metabolism of deep-sea creatures. Their chemical reactions proceed more slowly. They need less food. They move more slowly. They live longer. Some deep-sea animals can live for centuries or even millennia. The cold also affects the structure of their cell membranes. Membranes are made of fats, which can become stiff and brittle at low temperatures. Deep-sea creatures have evolved fats that remain fluid at cold temperatures. This allows their membranes to function properly. The scarcity of food is the final challenge. In the deep ocean, there is no sunlight, so photosynthesis is impossible. The primary source of food is the marine snow, the steady rain of dead organisms, fecal matter, and other organic debris that drifts down from the sunlit surface. This marine snow is a sparse and unpredictable food source. It can take weeks or even months for the particles to reach the sea floor. By the time they arrive, most of the organic matter has been consumed by other organisms. What remains is a lean and scattered meal. Deep-sea creatures have evolved to exploit this scarce food source. Many are scavengers, feeding on whatever they can find. Others are predators, hunting the scavengers. Still others are filter feeders, sieving the marine snow from the water. Many deep-sea creatures have slow metabolisms. They can survive on very little food. They can go for long periods without eating. Some can even enter a state of dormancy, reducing their metabolic rate to a fraction of normal. The combination of high pressure, low temperature, and scarce food has shaped the deep-sea ecosystem into something unique. It is a world of slow growth, slow reproduction, and long lifespans. It is a world where survival depends on efficiency and patience. But it is also a world of incredible diversity. There are thousands of species of deep-sea creatures, each adapted to a specific niche. There are fish with luminous lures, fish with transparent heads, fish with enormous jaws. There are jellies that trail tentacles for hundreds of feet. There are worms that live in the mud. There are crustaceans that scuttle across the sea floor. Each species is a masterpiece of evolution, a testament to the power of natural selection. They have been shaped by millions of years of adaptation to an extreme environment. They are the survivors of the deep. The deep sea is not a single environment. It is a series of different environments, each with its own set of challenges. There are the abyssal plains, vast and featureless. There are the mid-ocean ridges, volcanically active. There are the trenches, the deepest parts of the ocean. Each of these environments has its own unique community of organisms. The abyssal plains are home to worms, clams, and brittle stars. The mid-ocean ridges are home to hydrothermal vent communities. The trenches are home to amphipods and snailfish. The adaptations of deep-sea creatures are a testament to the incredible diversity of life on Earth. They show that life can survive almost anywhere, even in the most extreme environments. They remind us that we are part of a vast and interconnected web of life. Understanding the adaptations of deep-sea creatures is not just a matter of scientific curiosity. It has practical applications. The proteins and enzymes of deep-sea organisms are being studied for use in medicine, industry, and biotechnology. They may hold the key to new drugs, new materials, and new processes. The deep sea is a source of potential resources. It contains minerals, metals, and hydrocarbons. It also contains a wealth of biological diversity. Protecting this diversity is essential for the health of the planet and the well-being of future generations. So, the deep ocean is not just a place of mystery. It is a place of life, a place of adaptation, a place of resilience. And as we continue our exploration, we must strive to understand and protect it. In the next chapter, we will explore another aspect of deep-sea engineering. We will look at the machines that allow us to explore the deep. We will examine the evolution of the submersible, from the Bathysphere to the Alvin to the modern ROVs. We will see how technology has made it possible to go deeper, stay longer, and learn more.
But for now, let us appreciate the creatures of the deep. Let us marvel at their adaptations. Let us recognize the incredible resilience of life. And let us be humbled by the vastness and mystery of the ocean. The deep sea is a world of wonder. It is a world that we are only beginning to explore. And it is a world that we must protect for future generations. By the 1980s, the Alvin had proven itself as a reliable and versatile deep-sea research vessel. It had made thousands of dives and contributed to countless scientific discoveries. But the Alvin had its limits. It could only dive to about 15,000 feet. It could only stay down for about 8 hours. It could only carry 3 people. And it required a dedicated support ship. For many scientific questions, the Alvin was perfectly adequate. But for others, it was not. Scientists wanted to go deeper, stay longer, and collect more data.
They wanted to explore the hadal zone, the deepest part of the ocean, which extends from 20,000 feet to the bottom of the Mariana Trench. They wanted to study the geology, chemistry, and biology of these extreme environments. They wanted to understand how life could survive under such crushing pressure. To do this, they needed new machines. Machines that could go deeper than the Alvin. Machines that could stay down longer. Machines that could be controlled from the surface. Machines that could explore the deepest trenches of the ocean. The answer came in the form of remotely operated vehicles, or ROVs. These are unmanned submersibles connected to the surface by a cable. The cable provides power, data transmission, and a physical link. The ROV is controlled by a pilot on the surface using a joystick and a video monitor. ROVs have several advantages over manned submersibles. They are smaller and lighter. They can dive deeper. They can stay down for much longer periods.
They do not require life support systems. They can be operated in conditions that would be too dangerous for humans. The first ROVs were developed in the 1960s and 70s. They were primarily used for military and commercial purposes, such as inspecting underwater pipelines and searching for lost objects. But they quickly found their way into scientific research. By the 1980s, ROVs had become an essential tool for deep-sea exploration. They were used to discover hydrothermal vents, explore shipwrecks, and study the geology of the ocean floor. They could go where no human could go, and do what no human could do. One of the most famous ROVs is the Jason. Named after the mythological Greek hero, the Jason is a state-of-the-art vehicle that can dive to depths of over 20,000 feet. It is equipped with high-definition cameras, powerful lights, and a variety of scientific instruments. It has a mechanical arm that can collect samples and manipulate objects on the seafloor. The Jason is operated by the Woods Hole Oceanographic Institution, the same organization that operates the Alvin. It has been used for numerous scientific expeditions, including the exploration of hydrothermal vents in the Pacific Ocean, the discovery of new species in the Atlantic Ocean, and the study of deep-sea ecosystems in the Indian Ocean. Another notable ROV is the Nereus, a hybrid vehicle that can operate either as a conventional ROV or as an autonomous underwater vehicle, or AUV. In autonomous mode, it can travel independently of a cable, exploring vast areas of the seafloor. In ROV mode, it can be controlled directly, performing delicate tasks. The Nereus was designed to explore the deepest parts of the ocean, including the Mariana Trench. In 2009, it made a dive to the Challenger Deep, reaching a depth of over 35,000 feet. It was the first vehicle to do so since the Trieste in 1960. The Nereus collected samples and captured images of the seafloor, providing valuable data about this extreme environment. The Nereus was lost in 2014 during a dive in the Kermadec Trench near New Zealand. It was a tragic loss, but the vehicle had already made significant contributions to science. Its legacy lives on in the data it collected and the inspiration it provided. In addition to ROVs, there are also autonomous underwater vehicles, or AUVs. These are self-contained robots that can operate independently of a surface ship. They are programmed to follow a predetermined path, collecting data along the way. They can travel for hours or even days, covering vast areas of the ocean. AUVs are used for a variety of purposes, including mapping the seafloor, surveying marine life, and monitoring ocean conditions. They are particularly useful for exploring areas that are difficult to reach, such as under Arctic ice or in deep ocean trenches. The UVs have many advantages over ROVs. They are smaller and lighter. They can operate for longer periods. They can travel greater distances. And they do not require a cable, which can be a hindrance in certain environments. But UVs also have limitations. They cannot be controlled in real time. They cannot respond to unexpected events. They cannot collect samples or manipulate objects. For these tasks, ROVs are still preferred. The combination of ROVs and AUVs has revolutionized deep-sea exploration. These machines have allowed us to explore areas that were previously inaccessible. They have collected vast amounts of data. They have made new discoveries and opened up new frontiers. The technology of ROVs and AUVs continues to evolve. New materials, new sensors, and new control systems are constantly being developed.
These advances are making it possible to go deeper, stay longer, and collect more data than ever before. In the future, we may see even more advanced deep-sea robots. They may be able to explore the deepest trenches, sample the most extreme environments, and even return samples to the surface. They may be able to operate for months or years at a time. They may be able to work together in swarms, sharing information and coordinating their activities. The deep ocean is a vast and largely unexplored frontier. ROVs and AUVs are the tools that are helping us to explore it. They are the eyes and hands of scientists, extending our reach into the abyss. But even with these advanced machines, there is still a role for human exploration.
There is something irreplaceable about the presence of a person in the deep. The ability to see, to feel, to make decisions in real time. The ability to adapt to unexpected situations. The ability to bring back a first-hand account of the wonders of the deep. So, the future of deep-sea exploration will likely involve a combination of human and robotic exploration. ROVs and AUVs will do the heavy lifting, exploring the most difficult areas and collecting data. But humans will still be there, interpreting the data and making decisions. And occasionally, humans will still venture down into the deep to see for themselves what lies beneath. As we continue our journey, we will explore some of the discoveries that have been made with these machines. We will see the amazing creatures that live in the deep, the strange and beautiful landscapes of the sea floor, and the ongoing mysteries that still await us. The machines that go deeper are a testament to human ingenuity. They are the tools of our curiosity, and they are the means by which we will continue to explore the last great frontier on Earth.
We have now travelled through the sunlit surface waters, through the twilight zone where light begins to fade, through the midnight zone where darkness is absolute, and through the abyssal plains where the seafloor stretches endlessly into the gloom. But there is one more realm to explore, a realm so deep, so dark, and so extreme that it has its own name. It is called the hadal zone. The name comes from Hades, the ancient Greek god of the underworld. It is a fitting name for a place that seems so inhospitable. The hadal zone begins at a depth of about 20,000 feet, or roughly 4 miles down. It extends to the very bottom of the ocean, nearly 7 miles down in the deepest trenches. It is the deepest, darkest, and most extreme environment on Earth. The hadal zone is characterized by deep ocean trenches, which are long, narrow depressions in the seafloor. These trenches are formed by a process called subduction, where one tectonic plate is forced beneath another. As the plates converge, the ocean floor is pushed down into the Earth's mantle. This creates a deep trench that can extend for hundreds of miles. The deepest of all these trenches is the Mariana Trench, located in the western Pacific Ocean. It is nearly 37,000 feet deep at its deepest point, the Challenger Deep. That is over 7 miles down. To put that in perspective, if you placed Mount Everest at the bottom of the Challenger Deep, its summit would still be more than a mile underwater. The conditions in the hadal zone are extreme. The pressure is crushing, reaching over 15,000 pounds per square inch in the deepest parts. The temperature is near freezing, just a few degrees above 32 degrees Fahrenheit. The darkness is absolute, with no sunlight penetrating to these depths. Food is scarce, as the marine snow that drifts down from above is largely consumed before it reaches the hadal zone.
And yet, despite these extreme conditions, life exists in the hadal zone. There are creatures that have adapted to survive in this extreme environment. They are some of the most remarkable organisms on Earth. The most common animals in the hadal zone are amphipods, tiny crustaceans that resemble shrimp. Some species of amphipods can grow to over a foot long in the hadal zone, a phenomenon known as deep-sea gigantism. They scuttle along the seafloor, feeding on the sparse organic matter that accumulates there. There are also snailfish, which are small, pale fish that live near the bottom of the trenches. They have soft, gelatinous bodies that are adapted to the high pressure. They have no swim bladder, which would be crushed at those depths. They are some of the deepest living fish ever discovered. Other inhabitants of the hadal zone include sea cucumbers, which crawl slowly across the seafloor, and various species of worms.
There are also microbial communities, which play a crucial role in the hadal ecosystem. These microbes can break down the organic matter that accumulates in the trenches, recycling nutrients and supporting the food web. The hadal zone is also home to unique geological features. There are hydrothermal vents, which are cracks in the seafloor where superheated water, rich in minerals, erupts. These vents can support unique ecosystems, similar to those found at shallower vents. There are also methane seeps, where methane gas bubbles up from the seafloor, providing energy for chemosynthetic bacteria. The hadal zone is one of the least explored places on Earth. We have only a rudimentary map of the trenches. We have only a partial inventory of the species that live there. We have only a limited understanding of the geological processes that shape the region. But this is beginning to change. In recent years, advances in technology have made it possible to explore the hadal zone more systematically. ROVs and AUVs are now capable of reaching the deepest parts of the ocean. They are equipped with high-definition cameras, lights, and sampling equipment. They are providing us with a detailed look at this previously inaccessible world. One of the most ambitious hadal exploration projects was the 5 Deeps expedition, which took place in 2018 and 19. The expedition used a specially designed submersible called the limiting factor to dive to the deepest point in each of the 5 oceans. The limiting factor was a titanium sphere, similar to the Trieste, but much more advanced. The expedition successfully reached the Challenger Deep in the Mariana Trench, the deepest point in the Pacific Ocean. It also reached the bottom of the other 4 oceans, including the Atlantic, Indian, Southern, and Arctic. The expedition collected valuable data and samples, providing new insights into the hadal zone. Another notable hadal exploration project is the Hadal Exploration Program, a multi-institutional effort based in China. The program has deployed several ROVs to the Mariana Trench and other hadal regions. It has discovered new species, collected samples, and conducted detailed surveys of the seafloor. The hadal zone is also the focus of international scientific collaborations. Scientists from many countries are working together to explore and study this extreme environment. They are sharing data, technology, and expertise. They are working to build a comprehensive understanding of the hadal zone. The hadal zone is a fascinating and mysterious place. It is a realm of extremes, where life has adapted to survive under crushing pressure, near freezing temperatures, and perpetual darkness. It is a place of discovery, where new species and new ecosystems are still being found. It is a place of scientific importance, where we can learn about the geology of the Earth, the chemistry of the ocean, and the adaptations of life. The exploration of the hadal zone is also important for understanding the global ocean. The hadal zone plays a role in the global carbon cycle, the distribution of nutrients, and the circulation of water. It is connected to the rest of the ocean, and changes in the hadal zone can have far-reaching effects. The hadal zone is also a place of potential resources. It contains minerals, metals, and hydrocarbons. It also contains a wealth of biological diversity, which could be a source of new drugs, materials, and processes. But the hadal zone is also a fragile environment. The organisms that live there are slow-growing and slow-reproducing. They are vulnerable to disturbance. Human activities, such as deep-sea mining, could have a significant impact on the hadal zone. We must be careful to protect this unique and irreplaceable ecosystem. So, the hadal zone is a frontier. It is the deepest and most extreme environment on Earth. It is a place of mystery and discovery.
It is a place that we are only beginning to explore. As we continue our journey, we will explore the future of deep-sea exploration. We will examine the challenges and opportunities that lie ahead. We will consider the potential of new technologies and the importance of international cooperation. And we will reflect on the significance of the deep ocean for our planet and for our species. But for now, let us appreciate the hadal zone for what it is: a world of extremes, a place of wonder, and a testament to the resilience of life. By now, we have explored the depths of the ocean, from the sunlit surface to the hadal trenches. We have seen the creatures that live there, the ecosystems they form, and the discoveries that have been made. But we have not yet fully explored the machines that make this exploration possible.
How do we build vehicles that can withstand the crushing pressure of the deep? How do we design systems that can operate reliably in such an extreme environment? The answer lies in a combination of engineering principles, material science, and rigorous testing. Building a deep-sea submersible is not like building a car or an aeroplane. It requires a deep understanding of the physics of pressure, the properties of materials, and the challenges of operating in a hostile environment. Let us start with the most fundamental challenge: pressure. As we have discussed, the pressure in the deep ocean is immense. At the bottom of the Mariana Trench, the pressure is over 15,000 pounds per square inch. To put that in perspective, a typical car tire is inflated to about 35 pounds per square inch. The pressure in the deep ocean is more than 400 times that. To withstand this pressure, the hull of a submersible must be incredibly strong. It must also be shaped to distribute the pressure evenly. As we have seen, a sphere is the ideal shape for this purpose. The pressure is applied equally to all parts of the sphere, so there are no weak points where the pressure can concentrate. The material used for the hull is also critical. Early submersibles, like the Bathysphere, used steel. Steel is strong and relatively inexpensive, but it is also heavy. A steel sphere that can withstand deep-sea pressure must have thick walls, which makes the vehicle heavy and difficult to handle. Modern submersibles, like the Alvin, use titanium. Titanium is lighter than steel, but it is also stronger. It is resistant to corrosion, which is important in the saltwater environment, and it is non-magnetic, which is important for scientific instruments. The walls of the Alvin's pressure sphere are nearly 3 inches thick. This is thick enough to withstand the pressure at 15,000 feet, but thin enough to keep the vehicle buoyant. The sphere is carefully machined to exacting tolerances, so that it is perfectly spherical. The sphere is not a single piece of metal. It is welded together from several sections. The welds are critical. Any imperfection in the weld could compromise the integrity of the hull. The welds are inspected with X-rays and other non-destructive testing methods. The windows are another critical component. The windows of a deep-sea submersible must be strong enough to withstand the pressure, but transparent enough to allow the pilot and scientists to see out. They are typically made of acrylic or quartz, materials that are strong and transparent. The windows are thick and are mounted in a way that distributes the pressure evenly. The Alvin has several viewports, each about 4 to 5 inches in diameter. They are located at strategic points, providing the occupants with a good view of the outside. The windows are carefully tested to ensure they can withstand the pressure. The electrical systems of a submersible are also a major challenge. The high pressure can cause electrical components to fail. The salt water can cause corrosion. The cold temperatures can affect the performance of batteries and electronics. The electrical systems must be carefully designed and protected. The Alvin uses batteries for power,
The batteries are sealed in a pressure-tight container. The electrical wiring is routed through special connectors that are designed to withstand pressure. The electronics are housed in pressure-tight enclosures. The lighting system is also important. The deep ocean is completely dark, so the submersible must carry its own lights. The lights are mounted on the outside of the vehicle. They are powerful enough to illuminate the seafloor and the surrounding water. The Alvin has a sophisticated system of lights, including floodlights and spotlights. The lights are used for observation, photography, and videography. They can also be used to attract deep-sea creatures, which are often curious about bright lights. The control system is another critical component. The pilot must be able to control the submersible's movement precisely. The control system must be reliable and responsive. It must also be easy to use, even in the stressful environment of a deep dive. The Alvin has a variety of controls, including thrusters and a mechanical arm. The thrusters allow the vehicle to move in 3 dimensions. The mechanical arm allows the pilot to collect samples and manipulate objects on the seafloor. The buoyancy system is also important. The submersible must be able to descend and ascend in a controlled manner. It must also be able to hover at a specific depth. The buoyancy system uses ballast and variable ballast tanks to control the vehicle's position. The Alvin uses lead weights for ballast. When the vehicle is ready to descend, some of the ballast is released. When the vehicle is ready to ascend, more ballast is released. This provides fine control over the vehicle's buoyancy. The life support system is essential for manned submersibles. The occupants must have a supply of oxygen and a way to remove carbon dioxide. They must also have a way to control temperature and humidity. The life support system must be reliable and safe. The Alvin has a life support system that provides oxygen and removes carbon dioxide. The oxygen is stored in high-pressure tanks. The carbon dioxide is removed by a chemical scrubber. The temperature and humidity are controlled by a ventilation system. The communication system is also important. The submersible must be able to communicate with the surface. The communication system uses an acoustic link, which transmits sound waves through the water. It is not as reliable as a radio link, but it is the only option in the deep ocean. The Alvin has a sophisticated communication system.
It can transmit data and voice to the surface. It can also receive commands from the surface. The communication system is used for navigation, coordination, and emergency situations. All of these systems must be carefully integrated into the submersible. They must work together seamlessly. They must be reliable and safe. The design and construction of a deep-sea submersible is a monumental engineering challenge. The Alvin has been in service for over 50 years. It has been upgraded and modified many times. It is a testament to the robustness of its design. It is a testament to the skill of the engineers who built it. The Alvin is just one example of a deep-sea submersible. There are many others, each with its own unique design and capabilities. Some are larger, some are smaller. Some are manned, some are unmanned. Some are designed for shallow water, some for the deepest trenches. But all deep-sea submersibles share a common goal: to explore the ocean. They are the tools that allow us to see what lies beneath. They are the machines that make discovery possible. As we continue our journey, we will look to the future of deep-sea exploration. We will consider the new technologies that are being developed. We will explore the challenges and opportunities that lie ahead. And we will reflect on the significance of the deep ocean for our planet. For now, let us appreciate the machines that have made deep-sea exploration possible. They are a testament to human ingenuity and courage. They are the bridges between our world and the world below. And they are the tools that will continue to unlock the secrets of the deep. We have spent much of our journey exploring the physical environment of the deep ocean. The pressure, the cold, the darkness, the geology. But the deep ocean is not just a place of extreme conditions. It is also a place of life. A place where creatures have evolved in ways that seem almost alien.
A place where the ordinary rules of biology are rewritten. The creatures of the deep ocean are some of the most remarkable organisms on Earth. They have adapted to survive in an environment that would be lethal to most other forms of life. They have developed unique strategies for finding food, avoiding predators, and reproducing. They have taken on forms that are both strange and beautiful. Let us begin with the most iconic of deep-sea creatures, the anglerfish. The anglerfish is a predator that uses a bioluminescent lure to attract prey. The lure is a modified fin ray that extends from the fish's forehead. It is tipped with a light-producing organ that contains symbiotic bacteria. The bacteria produce a soft glow that attracts smaller fish and other prey. When a prey animal approaches the lure, the anglerfish strikes with lightning speed. Its jaws are enormous and its teeth are long and curved. It can swallow prey that is larger than itself.
The anglerfish is a master of ambush, perfectly adapted to the darkness of the deep. The anglerfish is not the only creature that uses bioluminescence. Many deep-sea organisms produce their own light. They use it for a variety of purposes, including attracting prey, avoiding predators, and finding mates. The light is produced by chemical reactions, often involving a molecule called luciferin. Some organisms, like the firefly squid, produce brilliant flashes of light. Others, like the jellyfish, produce a soft, continuous glow. Still others, like the vampire squid, can release a cloud of glowing particles to confuse predators. Bioluminescence is a common and diverse phenomenon in the deep ocean. Another remarkable group of deep-sea creatures is the tube worms. These worms live in hydrothermal vent communities, where they form dense colonies. They have no mouth, no stomach, and no digestive system.
Instead, they are filled with bacteria that convert the chemicals in the vent water into food. The tube worms provide the bacteria with a safe place to live, and the bacteria provide the tube worms with nourishment. The tube worms are a testament to the power of symbiosis. They are a partnership between two different organisms, each helping the other to survive. This partnership has allowed the tube worms to thrive in an environment that would otherwise be uninhabitable. The giant squid is another legendary creature of the deep. It is one of the largest invertebrates on Earth, reaching lengths of over 40 feet. It has enormous eyes, the size of dinner plates, which are adapted to detect the faintest traces of light. It has long tentacles, armed with suckers and hooks, which it uses to capture prey. The giant squid is a predator, feeding on fish and other squid. It is also a prey item for sperm whales, which dive to great depths to hunt them.
The giant squid is a creature of myth and mystery, and it has captured the human imagination for centuries. In recent years, scientists have been able to film giant squid in their natural habitat. These images have provided new insights into the behavior and biology of these elusive creatures. They have also inspired a new appreciation for the wonders of the deep. The deep ocean is also home to a variety of other unusual creatures. There are fish with transparent heads, like the barrel-eye, which can see through its own skull. There are fish with enormous jaws, like the gulper eel, which can swallow prey much larger than itself. There are fish with long, thin bodies, like the oarfish, which can reach lengths of over 30 feet. There are also a variety of invertebrates, including jellyfish, sea cucumbers, and brittle stars. These creatures come in a wide range of shapes, sizes, and colors. They are a testament to the incredible diversity of life on Earth.
The deep ocean is also home to a variety of crustaceans, including crabs, shrimp, and amphipods. Some of these crustaceans are adapted to the high pressure and low temperature of the deep. They have thick exoskeletons and slow metabolisms. They are often scavengers, feeding on the marine snow that drifts down from above. One of the most abundant deep-sea animals is the copepod, a tiny crustacean that is a key part of the food web. Copepods are eaten by a wide range of animals, including fish, squid, and whales. They are a crucial link in the transfer of energy from the surface to the deep. The deep ocean is also home to a variety of microorganisms, including bacteria and archaea. These microorganisms are the foundation of the deep-sea food web. They perform a wide range of functions, including breaking down organic matter, recycling nutrients, and producing energy through chemosynthesis. The microorganisms of the deep ocean are some of the most important organisms on the planet.
They play a crucial role in the global carbon cycle and the regulation of the Earth's climate. They are also a source of potential new drugs and industrial processes. The creatures of the deep ocean are not just interesting from a scientific perspective. They are also important for practical reasons. They are a source of food, medicines, and other resources. They are also an indicator of the health of the ocean. The deep ocean is a fragile ecosystem. The organisms that live there are slow-growing and slow reproducing. They are vulnerable to disturbance. Human activities, such as fishing, mining, and pollution, can have a significant impact on the deep-sea ecosystem. It is important that we protect the deep ocean and its inhabitants. We must use the resources of the deep sustainably. We must minimize our impact on the environment, and we must continue to explore and learn about this unique ecosystem.
The creatures of the deep ocean are a reminder of the incredible diversity of life on Earth. They are a testament to the power of evolution, and they are an inspiration to us all. As we continue our journey, we will explore the future of deep-sea exploration. We will consider the challenges and opportunities that lie ahead. We will reflect on the significance of the deep ocean for our planet and for our species. For now, let us appreciate the creatures of the deep. Let us marvel at their adaptations. Let us recognize their importance, and let us work to protect them for future generations. We have traveled a long way together. From the sunlit surface of the ocean, through the twilight and midnight zones, past the abyssal plains and the hadal trenches. We have seen the creatures that live in the deep, the ecosystems they form, and the machines that allow us to explore them. We have learned about the pressure, the cold, the darkness, and the incredible adaptations of life. But our journey is not yet complete. There is still much to explore, much to discover, and much to understand. The deep ocean remains one of the least explored regions on Earth. It is a frontier, a place of mystery and wonder, and it is a place that holds the key to many of the challenges facing our planet. In this chapter, we will look to the future. We will consider the new technologies that are being developed for deep-sea exploration. We will explore the scientific questions that remain unanswered, and we will reflect on the importance of the deep ocean for our planet and for our species. One of the most exciting developments in deep-sea exploration is the rise of autonomous underwater vehicles, or AUVs. These are self-contained robots that can operate independently of a surface ship. They are programmed to follow a predetermined path, collecting data along the way. AUVs have several advantages over traditional submersibles. They are smaller and lighter.
They can operate for longer periods, sometimes for days or even weeks. They can travel greater distances, covering hundreds of miles in a single mission, and they do not require a cable, which can be a hindrance in certain environments. AUVs are already being used for a variety of purposes, including mapping the seafloor, surveying marine life, and monitoring ocean conditions.
They are particularly useful for exploring areas that are difficult to reach, such as under Arctic ice or in deep ocean trenches. In the future, UVs may become even more capable. They may be equipped with advanced sensors, such as high-resolution sonar and imaging systems. They may be able to collect samples and return them to the surface. They may even be able to communicate with each other and coordinate their activities. Another exciting development is the emergence of new materials and manufacturing techniques. These are making it possible to build submersibles that are stronger, lighter, and more efficient than ever before. One of the most promising materials is titanium. Titanium is strong, lightweight, and corrosion-resistant. It is already used in many deep-sea submersibles, including the Alvin. In the future, titanium may be used in even more advanced applications, such as pressure hulls that are thinner and more efficient. Another promising material is carbon fiber. Carbon fiber is even lighter than titanium, and it is also very strong. It is already used in a variety of applications, including aircraft and sports equipment. In the future, it may be used in deep-sea submersibles, providing a new level of performance. Advances in manufacturing are also making it possible to build submersibles more quickly and more cheaply. 3D printing, for example, is being used to create complex components with high precision. This could reduce the cost of deep-sea exploration and make it more accessible to a wider range of scientists and institutions. New sensors and imaging systems are also being developed. These are allowing scientists to see the deep ocean in unprecedented detail. High-resolution sonar can create detailed maps of the seafloor. High-definition cameras can capture stunning images of deep-sea creatures. And advanced chemical sensors can detect trace amounts of substances in the water. In the future, these sensors may become even more sophisticated. They may be able to detect the faintest chemical signatures of life. They may be able to identify new species even before they are seen. They may be able to monitor the health of the ocean in real time. The scientific questions that remain unanswered are also a major driver of deep-sea exploration. There is still much that we do not know about the deep ocean. We do not fully understand the geology of the seafloor. We do not have a complete inventory of the species that live there. We do not fully understand the chemical processes that occur in the deep. One of the most pressing questions is the role of the deep ocean in the global climate system. The ocean absorbs a significant amount of carbon dioxide from the atmosphere. This helps to mitigate the effects of climate change. But the mechanisms by which the ocean absorbs carbon dioxide are not fully understood. The deep ocean in particular plays a crucial role in this process. Another important question is the origin of life on Earth. The hydrothermal vents of the deep ocean are considered to be a likely location for the emergence of life. The chemical and thermal conditions at these vents are similar to those that are thought to have existed on the early Earth. By studying the vents, we may be able to learn about the origins of life on our planet and the potential for life elsewhere in the universe. The deep ocean is also a potential source of valuable resources. It contains vast deposits of minerals, including manganese, copper, and nickel. It also contains hydrocarbons, including oil and gas. And it contains a wealth of biological diversity, which could be a source of new drugs, materials, and processes. The exploitation of these resources is a subject of debate. On one hand, they could provide economic benefits and help to meet the growing demand for raw materials. On the other hand, the extraction of these resources could have a significant impact on the deep-sea ecosystem. It is important to balance the potential benefits with the potential risks. The future of deep-sea exploration will also be shaped by international cooperation. The deep ocean is a global commons belonging to all of humanity. It is important that we work together to explore, study, and protect it. There are already several international organizations that are working on deep-sea issues. The International Seabed Authority, for example, regulates the exploration and exploitation of mineral resources in the deep ocean. The Intergovernmental Oceanographic Commission coordinates scientific research in the ocean, and the United Nations Convention on the Law of the Sea provides a legal framework for the use of the ocean. In the future, these organizations may become even more important. They may need to develop new rules and regulations to address the challenges of deep-sea exploration. They may need to provide a forum for international dialogue and cooperation. The future of deep-sea exploration is also a matter of public awareness and engagement. The deep ocean is often overlooked by the public, who are more familiar with the surface of the ocean and the land. It is important to raise awareness about the importance of the deep ocean and the challenges it faces. This can be done through education, outreach, and media coverage.
Documentaries, books, and articles can help to bring the wonders of the deep to a wider audience. They can inspire a new generation of explorers and scientists. The deep ocean is a vast and largely unexplored frontier. It is a place of mystery and wonder. It is a place that holds the key to many of the challenges facing our planet. And it is a place that we must protect for future generations. As we continue our journey, we will reflect on the significance of the deep ocean for our planet and for our species. We will consider the lessons we have learned and the challenges that lie ahead. And we will look to the future with hope and determination. And so we come to the end of our journey. We have traveled from the sunlit surface of the ocean down to the hadal trenches, the deepest places on Earth. We have seen the creatures that live there, the ecosystems they form, and the machines that allow us to explore them. We have learned about the pressure, the cold, the darkness, and the incredible adaptations of life. We have explored the history of deep-sea exploration, from the Bathysphere to the Alvin, to the modern ROVs and AUVs. And we have considered the future of this remarkable frontier. But our journey is not really an ending. It is a beginning. The deep ocean is still largely unexplored. There is still much to learn, much to discover, and much to protect. The deep ocean is a vast and mysterious place, and it holds many secrets. Let us take a moment to reflect on what we have learned. We have learned that the deep ocean is not a barren wasteland. It is a place of life, a place of incredible biodiversity. There are creatures that have adapted to survive in the most extreme conditions. There are ecosystems that are powered by chemical energy, not by sunlight. There are processes that shape the geology of our planet and influence the global climate. We have learned that the deep ocean is a place of extremes. The pressure is crushing, the temperature is near freezing, the darkness is absolute. And yet, life thrives there. The creatures of the deep are a testament to the power of evolution. We have learned that the deep ocean is a place of discovery. Every expedition brings new species, new ecosystems, and new insights. The deep ocean is one of the last frontiers on Earth, and it is a place of endless fascination. We have learned that the deep ocean is a place of engineering marvels. The machines that allow us to explore the deep are a testament to human ingenuity. They are the tools that have opened up this hidden world. We have learned that the deep ocean is a place of connection. It is connected to the rest of the ocean, to the atmosphere, and to the land. The deep ocean plays a crucial role in the global climate system, the carbon cycle, and the distribution of nutrients. We have learned that the deep ocean is a place of vulnerability. The creatures that live there are slow-growing and slow reproducing. They are vulnerable to disturbance. Human activities such as fishing, mining, and pollution can have a significant impact on the deep-sea ecosystem. And we have learned that the deep ocean is a place of hope. It holds the key to many of the challenges facing our planet. It is a source of potential resources, a repository of biological diversity, and a window into the past and future of our planet.
The deep ocean is a place of wonder. It is a place that inspires awe and curiosity. It is a place that challenges our assumptions and expands our understanding. It is a place that reminds us of the incredible diversity and resilience of life on Earth. The deep ocean is also a place of responsibility. We are the stewards of this planet, and we have a duty to protect the deep ocean and its inhabitants. We must use the resources of the deep sustainably.
We must minimize our impact on the environment. And we must continue to explore and learn about this unique ecosystem. The future of deep-sea exploration is bright. New technologies are being developed that will allow us to go deeper, stay longer, and collect more data. New partnerships are being formed between scientists, engineers, and policymakers. And new generations of explorers are being inspired to take up the challenge. But the future of deep-sea exploration also depends on us. It depends on our collective will to protect the ocean. It depends on our willingness to invest in scientific research. And it depends on our ability to work together across borders and disciplines. The deep ocean is a global commons. It belongs to all of humanity. It is a shared resource, a shared heritage, and a shared responsibility. We must work together to explore, study, and protect it. As we bring our journey to a close, let us remember the words of the great oceanographer Sylvia Earle. She said, "The ocean is the blue heart of the planet. It is the source of life, the regulator of climate, and the keeper of the planet's history." The deep ocean is a vital part of our planet. It is a source of life, a regulator of climate, and a keeper of history. It is a place of wonder, a place of discovery, and a place of hope. So, the next time you look out at the ocean, remember what lies beneath. Remember the pressure, the cold, and the darkness. Remember the creatures that thrive there, the ecosystems they form, and the machines that allow us to explore them. Remember the history, the science, and the wonder. And remember that we are all connected to this vast and mysterious place. The deep ocean is our final frontier. It is a place of endless discovery, and it is a place that we must protect for future generations. Thank you for joining me on this journey. I hope it has been as enlightening for you as it has been for me.
I hope it has inspired you to learn more about the deep ocean, to appreciate its beauty, and to support its protection. And I hope that, when you look at the ocean, you will see it not just as a body of water, but as a world of wonder. A world that is vast, mysterious, and full of life. A world that is worth exploring, understanding, and protecting. The deep ocean is a place of awe and inspiration. It is a place that has shaped our planet and our history, and it is a place that will continue to shape our future. So, let us continue to explore, let us continue to learn, and let us continue to protect this incredible, irreplaceable part of our planet.
And so we come to the end of our journey. We have travelled from the sunlit surface of the ocean down to the hadal trenches, the deepest places on Earth. We have seen the creatures that live there, the ecosystems they form, and the machines that allow us to explore them. We have learned about the pressure, the cold, the darkness, and the incredible adaptations of life. We have explored the history of deep-sea exploration, from the Bathysphere to the Alvin to the modern ROVs and AUVs. And we have considered the future of this remarkable frontier. But our journey is not really an ending.
it is a beginning. The deep ocean is still largely unexplored. There is still much to learn, much to discover, and much to protect. The deep ocean is a vast and mysterious place, and it holds many secrets. Let us take a moment to reflect on what we have learned. We have learned that the deep ocean is not a barren wasteland. It is a place of life, a place of incredible biodiversity. There are creatures that have adapted to survive in the most extreme conditions. There are ecosystems that are powered by chemical energy, not by sunlight. There are processes that shape the geology of our planet and influence the global climate. We have learned that the deep ocean is a place of extremes. The pressure is crushing, the temperature is near freezing, the darkness is absolute. And yet, life thrives there. The creatures of the deep are a testament to the power of evolution. We have learned that the deep ocean is a place of discovery. Every expedition brings new species, new ecosystems, and new insights. The deep ocean is one of the last frontiers on Earth, and it is a place of endless fascination. We have learned that the deep ocean is a place of engineering marvels. The machines that allow us to explore the deep are a testament to human ingenuity. They are the tools that have opened up this hidden world. We have learned that the deep ocean is a place of connection. It is connected to the rest of the ocean, to the atmosphere, and to the land. The deep ocean plays a crucial role in the global climate system, the carbon cycle, and the distribution of nutrients. We have learned that the deep ocean is a place of vulnerability. The creatures that live there are slow-growing and slow reproducing. They are vulnerable to disturbance. Human activities such as fishing, mining, and pollution can have a significant impact on the deep sea ecosystem. And we have learned that the deep ocean is a place of hope. It holds the key to many of the challenges facing our planet. It is a source of potential resources, a repository of biological diversity, and a window into the past and future of our planet. The deep ocean is a place of wonder. It is a place that inspires awe and curiosity. It is a place that challenges our assumptions and expands our understanding. It is a place that reminds us of the incredible diversity and resilience of life on Earth. The deep ocean is also a place of responsibility. We are the stewards of this planet, and we have a duty to protect the deep ocean and its inhabitants. We must use the resources of the deep sustainably. We must minimize our impact on the environment. And we must continue to explore and learn about this unique ecosystem. The future of deep-sea exploration is bright. New technologies are being developed that will allow us to go deeper, stay longer, and collect more data. New partnerships are being formed between scientists, engineers, and policymakers. And new generations of explorers are being inspired to take up the challenge. But the future of deep-sea exploration also depends on us. It depends on our collective will to protect the ocean. It depends on our willingness to invest in scientific research. And it depends on our ability to work together across borders and disciplines. The deep ocean is a global commons. It belongs to all of humanity. It is a shared resource, a shared heritage, and a shared responsibility. We must work together to explore, study, and protect it. As we bring our journey to a close, let us remember the words of the great oceanographer, Sylvia Earle. She said, "The ocean is the blue heart of the planet. It is the source of life, the regulator of climate, and the keeper of the planet's history." The deep ocean is a vital part of our planet. It is a source of life, a regulator of climate, and a keeper of history. It is a place of wonder, a place of discovery, and a place of hope. So, the next time you look out at the ocean, remember what lies beneath. Remember the pressure, the cold, and the darkness. Remember the creatures that thrive there, the ecosystems they form, and the machines that allow us to explore them. Remember the history, the science, and the wonder. And remember that we are all connected to this vast and mysterious place. The deep ocean is our final frontier. It is a place of endless discovery. And it is a place that we must protect for future generations. Thank you for joining me on this journey. I hope it has been as enlightening for you as it has been for me. I hope it has inspired you to learn more about the deep ocean, to appreciate its beauty, and to support its protection. And I hope that, when you look at the ocean, you will see it not just as a body of water, but as a world of wonder. A world that is vast, mysterious, and full of life. A world that is worth exploring, understanding, and protecting. The deep ocean is a place of awe and inspiration. It is a place that has shaped our planet and our history. And it is a place that will continue to shape our future. So, let us continue to explore. Let us continue to learn. And let us continue to protect this incredible, irreplaceable part of our planet. For most of human history, the ocean floor was a complete mystery. People knew that the ocean was deep. Sailors had dropped weighted lines over the side of their ships for centuries, measuring depth in fathoms, where 1 fathom equals 6 feet. But these measurements were rare, scattered, and often inaccurate. The ocean was simply too vast. The idea of mapping the seafloor seemed almost impossible. Think about what it means to map a surface you cannot see. On land, you can walk across a landscape, climb its mountains, cross its valleys. You can see where you are going. You can draw what you observe. But the ocean floor is hidden beneath miles of dark water. You cannot see it. You cannot walk on it. You can only measure it indirectly, by dropping a line or sending down a sound wave. The first systematic attempt to map the ocean floor began in 1872. It was called the Challenger Expedition, and it was one of the most ambitious scientific voyages in history. The HMS Challenger was a British naval vessel converted into a research ship. It was equipped with laboratories, dredges, and sounding equipment. Its mission was to explore the world's oceans and collect data about their depth, temperature, chemistry, and biology. Over the course of 4 years, the Challenger sailed nearly 70,000 miles. It visited every ocean except the Arctic. The crew took soundings at more than 360 stations, measuring the depth of the ocean at each location. They used a simple but effective method. A weighted rope lowered over the side of the ship until it touched the bottom. The length of the rope told them the depth. It was painstaking work. Each sounding took hours. The rope had to be lowered slowly to prevent it from tangling. The ship had to stay in position, which was difficult in rough seas, and the readings were often imprecise. The rope could be pulled sideways by currents. The weight could sink into soft mud. The depth could be off by hundreds of feet. Despite these challenges, the Challenger expedition produced a remarkable data set. It revealed that the ocean floor was not flat, as many had assumed. There were mountains, valleys, and vast plains. There were regions where the depth changed dramatically over short distances. One of the most important discoveries came in March 1875. The Challenger was sailing in the western Pacific Ocean, near the Mariana Islands.
The crew lowered the sounding line, and it kept going, and going, and going. The line reached nearly 27,000 feet before it hit the bottom. It was the deepest sounding ever recorded. The site was named the Challenger Deep, after the ship that discovered it. The Challenger Deep remained the deepest known point in the ocean for nearly a century. It was not until 1960 that humans would finally reach its bottom. But the Challenger expedition had done something even more important.
It had shown that the ocean floor was a place of remarkable variety and complexity. The expedition also collected biological samples from the deep. They dredged the bottom and brought up creatures that had never been seen before. Some were strange and alien, with eyes that seemed too large for their heads and bodies that were almost transparent. The Challenger expedition discovered over 4,700 new species. It was a revelation. The deep ocean was not a desert. It was a world of life. The Challenger expedition also laid the foundation for modern oceanography. It established the importance of systematic observation, careful measurement, and international collaboration. It inspired a generation of scientists and explorers, and it showed that the ocean was a frontier worth exploring. But the Challenger expedition was just the beginning. Mapping the ocean floor would require new tools that could measure depth faster, more accurately, and over larger areas.
One of the most important of these tools was the echo sounder. The echo sounder uses sound waves to measure depth. A sound pulse is sent down from the ship. It travels through the water, bounces off the sea floor, and returns to the ship. By measuring the time it takes for the sound to return, you can calculate the depth. The echo sounder was developed in the early 20th century. It was a breakthrough. Instead of taking hours to make a single measurement, the echo sounder could make thousands of measurements in a day. It could map the seafloor in detail, revealing features that had been completely unknown. One of the first major discoveries made with the echo sounder was the Mid-Atlantic Ridge. This is a massive underwater mountain range that runs down the middle of the Atlantic Ocean. It is over 10,000 miles long. It is the longest mountain range on Earth. And it was completely invisible until the echo sounder revealed it. The discovery of the Mid-Atlantic Ridge was a turning point in geology. It provided evidence for the theory of plate tectonics, which explains how the Earth's crust is constantly moving. The ridge is where new crust is formed, as magma rises from the Earth's interior and pushes the plates apart. It is a place of great geological activity, with earthquakes, volcanoes, and hydrothermal vents. The mapping of the ocean floor also revealed other remarkable features. There are deep ocean trenches, where one plate is forced beneath another. There are underwater volcanoes, called seamounts, which rise thousands of feet from the seafloor. There are vast abyssal plains, covered in a thick layer of sediment. There are canyons, ridges, and fracture zones. All of this was hidden beneath the waves, unknown to humanity until the tools to see it were developed. One of the most important figures in the history of mapping the ocean floor was Marie Tharp. She was a geologist and oceanographer who worked at Columbia University in the 1950s and 60s. Her work was groundbreaking. Tharp was part of a team that was creating maps of the ocean floor. She took the raw data from echo sounders and other instruments and turned it into detailed charts. She worked in a small office, surrounded by rolls of paper and stacks of data. She drew the maps by hand, carefully plotting the contours of the seafloor. Tharp's maps revealed something astonishing. The Mid-Atlantic Ridge, which had been discovered earlier, was not a simple ridge. It was a complex system of ridges, valleys, and fault lines. And in the center of the ridge, there was a deep valley, a rift, where the Earth's crust was being pulled apart.
This was a crucial piece of evidence for the theory of plate tectonics. It showed that the ocean floor was not static. It was moving. The continents were drifting. The Earth was alive. Tharp's work was initially met with skepticism.
Many scientists did not believe in plate tectonics. They thought the ocean floor was stable and unchanging. But Tharp's maps were so detailed and so convincing that they eventually won over the scientific community. She is now recognized as one of the pioneers of modern oceanography. The mapping of the ocean floor has continued to advance. In the 1970s and 80s, multi-beam sonar was developed. This technology uses multiple sound beams to create a detailed, three-dimensional image of the sea floor. It can map large areas quickly and accurately. Today, we have satellites that can measure the ocean floor from space. They do not see the seafloor directly, but they can detect subtle variations in the Earth's gravity. These variations are caused by the shape of the seafloor. Mountains and ridges have stronger gravity, while trenches have weaker gravity. By measuring these variations, scientists can create a rough map of the ocean floor.
But even with all this technology, we have only mapped a small fraction of the ocean floor in detail. According to some estimates, more than 80% of the ocean floor remains unmapped. There are vast areas that have never been seen by human eyes or instruments. This is a remarkable statistic. We know more about the surface of Mars than we do about the bottom of our own ocean. The ocean floor is the largest and least explored environment on Earth. It is a frontier that is still waiting to be discovered. The mapping of the ocean floor is not just an academic exercise, it has practical applications. It helps us understand the geology of our planet. It helps us predict earthquakes and tsunamis. It helps us find resources such as oil, gas, and minerals. It helps us protect marine ecosystems and manage fisheries. And it helps us understand our place in the universe. The ocean floor is a record of Earth's history.
It contains evidence of past climate change, past mass extinctions, and past geological events. By studying it, we can learn about the past and prepare for the future. So, the next time you look at a map of the world, remember that the blue areas are not empty. They are full of mountains, valleys, and plains. They are full of life, geology, and history. They are full of mysteries that are still waiting to be solved. The mapping of the ocean floor is one of the great scientific achievements of the modern era. It has transformed our understanding of our planet, and it has opened up a new frontier for exploration. A frontier that is dark, deep, and full of wonder. The ocean floor is calling, and we are only beginning to answer. The deep ocean is beautiful, mysterious, and full of wonder. But it is also unforgiving. It does not care about your intentions, your courage, or your technology. It only cares about the laws of physics. And when something goes wrong in the deep, it goes wrong very, very quickly. Throughout the history of deep-sea exploration, there have been disasters, tragedies that have cost lives, destroyed equipment, and shaken the confidence of those who venture into the abyss. But from each disaster, there have been lessons. Lessons that have made us safer, wiser, and more respectful of the ocean's power. Let us begin with one of the most famous and most tragic disasters in the history of submarine exploration: the loss of the USS Thresher. The Thresher was a nuclear-powered attack submarine of the United States Navy. It was one of the most advanced submarines of its time, designed to hunt other submarines and protect aircraft carriers. It was fast, quiet, and heavily armed. On April 10, 1963, the Thresher was conducting deep diving tests off the coast of New England. It was accompanied by a support ship, the Skylark, which maintained communication with the submarine via underwater telephone. The Thresher descended to its test depth of 1,300 feet. Everything seemed normal. Then, at 9 in the morning, the Skylark received a message from the Thresher. It was garbled and incomplete, but it seemed to indicate that the submarine was experiencing some problems. The message ended with the words, "exceeding test depth." The Skylark waited for further communication. None came. The Thresher had vanished. It was gone. A massive search operation was launched. Ships, planes, and submarines scoured the area. But the ocean is vast, and the Thresher was deep. It took several months to find the wreckage, lying on the seafloor at a depth of over 8,000 feet. The investigation that followed revealed a tragic sequence of events. A pipe fitting in the submarine's engine room had failed.
Water had sprayed into the compartment, causing a short circuit. The short circuit had shut down the submarine's reactor, cutting off power. Without power, the submarine could not surface. It continued to descend until the pressure crushed it. The loss of the Thresher was a devastating blow to the United States Navy. It was the first nuclear submarine to be lost, and it took with it all 129 crew members. It was also a wake-up call. In response to the disaster, the Navy established the SubSafe program. This program was designed to improve the safety of submarines through better design, better materials, and more rigorous testing. Every component of every submarine was inspected and certified. The program was strict and unforgiving, but it worked. Since SubSafe was implemented, no American nuclear submarine has been lost. The Thresher disaster also highlighted the dangers of the deep ocean. It showed that even the most advanced technology can fail under the extreme conditions of the abyss. And it showed that the ocean is not a place to be taken lightly. Another tragedy that shook the world was the loss of the Russian submarine Kursk in August of 2000. The Kursk was a nuclear-powered cruise missile submarine, one of the largest and most powerful submarines ever built. It was on a training exercise in the Barents Sea when it suffered a catastrophic explosion. The explosion was caused by a faulty torpedo. The torpedo's fuel had leaked and ignited, causing a massive blast that ripped open the submarine's hull. The Kursk sank to the bottom at a depth of about 350 feet. The Russian Navy initially claimed that the submarine had suffered a minor problem and that the crew was safe. But as the hours passed, it became clear that something had gone terribly wrong. The crew was trapped inside the submarine with limited oxygen and no way to escape. An international rescue effort was launched. British and Norwegian rescue teams arrived with specialized equipment. But the Russian Navy was slow to accept help. Valuable time was lost. By the time the rescue teams were able to reach the submarine, it was too late. All 118 crew members had died. The Kursk disaster was a tragedy that shocked the world. It was a reminder that even the most powerful militaries can be humbled by the ocean. And it highlighted the importance of international cooperation in rescue operations. The lessons of the Kursk led to improvements in submarine safety, including better emergency escape systems, better communication equipment, and better international coordination. But the deep ocean does not only claim submarines. It has also claimed submersibles, the very machines we rely on to explore the abyss. One of the most famous incidents involving a submersible was the sinking of the Alvin in 1968. The Alvin was the workhorse of American deep-sea research, and it had already made many successful dives. On October 16, 1968, the Alvin was preparing for a dive off the coast of Cape Cod. It was being lowered into the water from its support ship when a cable snapped. The Alvin plunged into the ocean and sank to the bottom,
at a depth of nearly 5,000 feet. The Alvin was lost. It was a devastating blow to the Woods Hole Oceanographic Institution, which operated the submersible. But there was a glimmer of hope. The Alvin was sitting upright on the sea floor. Its pressure sphere was intact. The submersible was not destroyed. The question was whether it could be recovered. Recovering a submersible from 5,000 feet was not a simple task. It required specialized equipment and careful planning. But Woods Hole was determined. The recovery operation took nearly a year.
A specially designed cable was lowered to the Alvin, and a hook was attached to its frame. Then, slowly, carefully, the Alvin was lifted back to the surface. The recovery was a success. The Alvin was brought back to the surface, repaired, and returned to service. It continued to make dives for decades, and it is still operational today. The Alvin incident taught several important lessons. It showed that submersibles can survive even a catastrophic loss of support. It showed that recovery is possible with the right equipment and the right planning. And it showed that even the best machines can fail, but that doesn't mean they have to be abandoned. The Alvin incident also highlighted the importance of redundancy. The Alvin had backup systems for many of its critical functions. Its pressure sphere was designed to withstand pressure even if the hull was compromised. These design features contributed to its survival and recovery. More recently, the loss of the Titan submersible in June of 2023 shocked the world. The Titan was a submersible operated by a private company, OceanGate. It was designed to take tourists to the wreck of the Titanic, which lies at a depth of about 12,500 feet. On June 18, 2023, the Titan began its descent to the Titanic. It was carrying 5 people. After about 1 hour and 45 minutes of descent, the Titan lost contact with its support ship. A massive search operation was launched. Ships, planes, and sonar equipment were deployed to find the Titan. But the ocean was vast, and the search area was large. After several days of searching, the wreckage of the Titan was found. The submersible had suffered a catastrophic implosion, likely caused by a failure of its pressure hull. The implosion would have been instantaneous and would have killed all 5 occupants. The Titan disaster was a tragic reminder of the risks of deep-sea exploration. It showed that even with modern technology, the deep ocean remains a dangerous place. It also raised questions about the safety of commercial deep-sea tourism and the regulation of submersible operations. The lessons from all of these disasters are clear. The deep ocean is a place where caution is essential. Designs must be robust, materials must be tested, procedures must be followed, and emergency plans must be in place. But there is also a broader lesson. The deep ocean is a place where mistakes are costly. It is a place where hubris can be fatal. It is a place where nature will always have the last word. And yet, despite these dangers, we continue to explore. We continue to build new machines, to push the boundaries, and to seek the wonders of the abyss. Why? Because the ocean is a part of us. It is where life began. It is where our planet's history is written, and it is where our future may be found. The disasters of the deep are not reasons to stop exploring. They are reasons to explore more carefully, more wisely, and more respectfully. They are reminders of the ocean's power and our own fragility, and they are opportunities to learn. So, let us honor the men and women who have lost their lives in the pursuit of knowledge. Let us learn from their sacrifice, and let us continue to explore the deep with the caution and courage it deserves. The abyss is waiting, and it will always test us. But it will also reward us with wonders beyond imagination.